Dude, I have a
And then you have to do it in a
4-hour-long
round.
interview.
Yeah, you have to
They
keep
were
following
supposed to send me the schedule. Dude, with BD. They made me 4 hours for it because
it's the same guy, at least it's the same class structure.
I did the 15-minute one after the career fair. Then I did the 15-minute online coding assessment. Then I did the hour-long panel with 2 people where they had me live code for 40 minutes.
Oh my god.
Yeah, and now we have your schedule open tomorrow from 9 a.m. to 1 p.m. and we'll send you a schedule on Monday. I'm like,
That was something like this.
I know. What? I'm a new grad. What the hell? Like, what do you need me for 4 hours for? So genuinely. What the hell?
Yeah.
Of the project. Which I mean, yeah, the project's 35%. Yeah, but that means that the milestone is worth 0%.
All right, let's get started. Let's see. Today you have homework due. This is going to be a packed list here. Project proposal resubmissions are due Wednesday this week. Please have a separate document just so I can see. So when I go look through those, if I have any questions, I know which one is your current version. I don't get confused. Student presentations are about to start. So I talked to most of the project groups when I saw them. So you will be assigned some topic related to your project. I did my best to kind of load balance and get everybody something that was related. The topics haven't been assigned. You can see the website. If they're insane and you have no idea, well, first of all, if you have no idea what it is, that's okay. Come ask me. I'll tell you what I mean by it. There could be some miscommunication there. But if it's completely unrelated to your project, I may have made an error. Come and let me know. You're going to have to sign up for a review, a presentation review with me, Matt, or James, like the week before or sometime before the presentation. Just to be about 30 minutes. You give your talk, you get feedback on it. Those dates I don't have available for you yet. I should have them by Wednesday, our next meeting. And then the presentation schedule is on the topic assignment sheet. So for those people that have to give a presentation the Monday after the midterm, boy, that's kind of mean, isn't it? That's just mean. I'll if you're having trouble with those timelines, let me know. I can make available a Zoom meeting on Saturday or Sunday, so at least it's not as stressful. But you have 2 weeks, so maybe you can get to it beforehand. When I post the time schedules, we can talk afterwards on Wednesday if you're in that group. Let's see. Any questions about presentations? Yeah.
So what if we have like a topic that like we haven't implemented into our project yet?
That's fine. This will help you get ready for that. So we're not like at the details of like which register do you do, right? It could be just introducing some of these topics at a high level. So people like optical communication, there's some people that are doing that. Like, what does that even mean? How does that work? And then you could get down to working down to the level of how you interface it with your microcontroller. Yeah.
I meant that, like, from previous semesters, do people, does everyone show up for everybody's presentations?
Oh yeah, it's part of the graded experience. I've taught to 7 people before. It sucks. Then when I taught 370 during the pandemic, that was awesome. Well, yes, you will need to be here for a presentation. You're going to be grading. So there's going to be peer grading for this, so everybody will grade the presentations. Any other questions? Okay, great. Homework 7 is assigned and due in about a week. And then the exam will be on Friday the 11th, 4:30 to 7:30 or 6:30 in Bicester, and then in Bicester, just down the hallway in the big auditorium, and then there's a room next to it, I believe. That's the 39 or 1690. And then student presentations happen after that. So any logistics questions in the next couple of weeks? Yeah.
I was just wondering when the ADC lecture from last week might be declassified.
Oh. I like that. I'll take a note to do it today.
Thank you.
Yep. Any other questions? Yeah. What's that?
Never mind,
Cool.
I see it.
So analog slides. All right, anything else? Great. All right, so now we'll talk about this week, we're basically talking about the details of analog to digital converters and digital to analog converters. Okay, so we'll start off with ADCs. Good reference material. I mean, as you guys are starting to see, there's lots of great reference material on the internet. People use embed systems all the time. These are two particular places. So the STM reference manual has a detailed section. You can almost read that whole thing and understand, but if you want higher level information, the embedded systems, ARM Cortex-M3 or M, this book is pretty good. There's also good tutorials online. So today we're going to talk about sample and hold circuits, 3 different types of ADCs that you're likely to encounter, and then ADCs on your particular dev kit. So again, this is basically your job is to make something that's like an oscilloscope. It's going to sample analog signals. In theory, it's not much different, except for this has wider bandwidth, better voltage tolerances. I mean, it's better in all ways, but a 10-bit ADC, I mean, this is not that impressive, just 10 bits, right? It's just that this thing can go fast and is accurate, benchtop quality. So one of the fundamental building blocks here of ADCs are sample and hold circuits. So the job of these circuits is to capture and hold some analog voltage. So because it usually takes time. You'll see later on in later circuits, it takes time to actually converge on some digital approximation for the circuit. And so what you need is capture a version of that. So in this simplified version, you have some op amp, you have some analog input, you have an op amp, and then you have a switch here. So the op amp's going to go and charge up that capacitor, and then you disconnect it. And now the analog voltage can swing over here, but there's a version of this captured here. This is only reduced or limited by its leakage current. And then the op amp will push that out, and now you can have this sampled version of it. Yep. Yeah, there are much in real world analog sample hold circuits. They are more complicated, and they have a finite amount of time. But usually the time isn't that long. We're not trying to hold a circuit or an analog voltage for minutes. A couple microseconds to milliseconds is usually enough. All right, so we'll go here. This is an example of a sample hold circuit. So this is just a transmission gate. Basically, it's an NMOS and PMOS pair, and it's going to pass the voltage on the input through it when it's been opened. So here, I can turn this thing on, and we see there's some analog input. So we can see the blue here highlights the signal, some oscillating signal, and we're going to go sample it. And you can see it passing through. Let's see, what's this node? This node is here. So when I hold it down, I'm doing the sampling phase, and then I can hold it just like that. And this, in this particular case, is going to last forever. Or, oh no, it's actually decaying slightly. Oh, that's kind of cool. I wonder why. Probably these are not ideal op amps. That's probably the reason. All right. Any question about how this works or why in the world we need it? Okay. So in real world systems, in FalSat, it ramps up very quickly. You may have seen it, but the analog sine wave that was going in is kind of like immediately captured on the op amp or on that capacitor, which isn't the case in the real world. Usually there is some amount of charge up time. So almost, you'll see this idea over and over again through this lecture. You have some DC signal. This is some sensor you have, and it has some inherent resistance in it, some series resistance, which means it's limiting its drive strength. It can't perfectly charge up a capacitor instantaneously. It's not possible. And so what you end up having is some RC charge up time. And so that means that even for a sample and hold circuit, there's some sort of sample time. Sample time can't be infinitely small. It has to be something while you allow that capacitor to charge up. So it's nice in the sense that many microcontrollers allow this to be programmable. So you could have, if you make your sampling time smaller, then you can go faster, but you may have inaccurate results, right? It may be that you haven't charged up all the way. So when can you fake it? Under what conditions? If you know you're going to get errors, under what conditions would you choose to make it smaller than probably the maximum? And I take 30 minutes, talk to yourself. Why do they even give you this option? Why does STM give you an option to make sampling time smaller, knowing that it might come with inaccurate solutions? Go ahead.
It is more important to you than accuracy. Yeah, it's something less accurate. I don't know why you would want to do that. If you need to do analog stuff and your data faster, and if you're off by a couple sort of measurements per second, I don't know, millimeters or milliseconds, then it doesn't matter as much as getting the data as fast as you can. Because yeah, if you're looking for a waveform, as opposed to the exact.
What do you think? Why is this a programmable feature on your STM32? Yeah.
Like sometimes you don't care about the precision of the thing. If you just want to see that your thing is spitting out some voltage and that's all you need for your event, like it's probably good enough. Like if it's a piezo sensor and you just like slam on it, you don't really care if it's like 0.3 or 0.6 volts coming out.
That's true. That's true. Okay. What are some other factors, other than I just don't care that much about resolution or accuracy? What are some other factors that knowing something about your sensor would allow you to choose a different time scale for sampling? Yeah.
The sensor has a lower accuracy than.
The sensor itself is not just that you want a lower accuracy, it's that your sensor itself is just poor.
Yeah.
And so, okay, if I know something about my sensor, okay, that's fine. Anything else? What about if you want to sample as fast as you can and you want it to be accurate and the sensor is accurate? What's another factor? Yeah. These are all great answers. Somehow I have not set you up for success by beaming into you this secret answer I'm looking for. That's fine, no problem. Part of this is because of this R here. There's a resistor that's limiting how much current can be pushed through. If that resistor was really large, it would take a long time to charge up. If that resistor happens to be small because of your circuit design, then you can sample it. It'll take, if the resistor is small, more current can flow in, and then this curve will be much sharper. And so you'll asymptote towards the answer much faster. And so the point is, if you know your source resistance of your sensor is small, then you can adjust the sampling frequency or sampling window to be smaller. Okay? Does that make sense? Okay. All right, let's talk about some more ADC building blocks here. Okay? So comparators, right? So comparators, like an op-amp, it's an analog component. We don't care about how it works internal, that's too complicated. But basically you can say, if I have two inputs, it'll tell me if the positive is higher or lower than the input. So for instance, if the voltage on the positive is larger than the voltage on the negative, it's high. If it's positive is smaller than negative, it's low on the outside. Okay, so it's just this fundamental unit that compares two signals and gives you a binary output. Is this higher or lower? So that's, any questions about, yeah?
By high, you mean VSS, like the positive VSS is the output?
Yeah.
Okay.
Yeah, or VC, yeah, in this case it's, so you'll see different, that's a good point. In this particular diagram, the power nodes here have been indicated by positive VSS and negative VSS, and sometimes it would be ground and VDD. Electrical engineers can't come to agreement on exactly what nomenclature they want to use because they're all came from different places. That's fine. So here we're just saying the negative rail, the lowest possible voltage this thing will deal with is negative VC or VSS, and then you have positive VSS. And so what I mean by high or low is just, yeah, is it all the way to the max or always to the minimum? And then we have the voltage divider. In this class, we don't care about doing the calculations necessarily, although it is probably good to remember the voltage divider formula. Here we're saying that we have two resistors. They could be the same value or they could be different value. We're showing that voltage comes in, and then I can get some variation or some version of the analog voltage by this equation. And if it happens to be that the two R's are the same, you get 50%. Okay? So now I have a way to test voltages, okay, whether two voltages. And now I have a way to manipulate voltages to give me a percentage of the incoming voltage. So those two things can come together and provide us with these building blocks. And so the simplest one would be like a 1-bit ADC. Now this, you could just use a inverter for this or a buffer, some digital logic point, but for the purpose of this example here, we've got two R's, so R and R, meaning that the voltage from VCC on Vref here is 50%, okay, 50% VCC, and I have V in here, and so you can see this little diagram here. We have V in coming, is increasing as a function of time. It gets over the threshold, the output is high, and then the output is low again as it comes back down. So I made a 1-bit ADC, and if you're clever, you could go and change the R ratio to now you could test different values. Okay, great. Any questions so far? All right. One thing that's always painful when you look at these diagrams, you got to remember which one's positive and which one's negative. Sometimes they flip around, like on the next slide, they're going to be flipped around. All right, so one of the most basic and fundamental ADC architectures is the flash ADC. This is made up of a voltage ladder. So here we can see these resistors here. They're in a ladder structure, and you can go through and do the math and figure out that each one of these is a set interval over the entire space. So for instance here, it's just Vref divided by the number of resistors, so you get a 6/5 or 6/7, 5/7, 4/7, blah, 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 all the way through. Basically, we're making different versions of the input reference. Then we use a bunch of comparators. We use all these different comparators to compare, is the input signal, V in, greater or less than 1/7 of my reference voltage? Now I can just go through and just calculate what it is, and I need an encoder here to turn it back into binary. But it's basically just like a level sensor. I've got this tree. What? This tree here is making me kind of like levels of a jug, let's say. It's giving me all these little gradations, and then Vn is the level of the water. I'm just comparing. Is this value that I have in here equal to this measurement label on the outside? And then use a priority encoder to encode this into binary. Any questions on the structure? Yeah.
Oh, so the reference in this case, instead of using like ground like before in a simple ADC, you would set it to a more like informative one to see exactly where you're at. Is that good?
The reference is, remember we made the diagram that was like, here's some analog voltage from here to here, and then it turned into binary. And we had to choose what was the top reference voltage and what was the bottom reference voltage. So here, the bottom reference voltage is ground. And then the top reference voltage is this value, Vref. And I could, where do you get Vref from? So Vref could be your power supply. That's a little bit noisy, but that's what most ADCs on a microcontroller default to. Sometimes they have internal references, and that's a very well-known stable voltage. That's another way to do it. Does that answer your question? Okay, well, let's see. Let me see if I can confuse you more enough on the next slide such that you ask another question, then we'll get right to it. All right, so here's the example. So in Fallstad, right, we have, the color gradations are just indicating the reference to ground, or the voltage to ground, right? So here ground is gray, and then each one of these things is, you can see it, the thing will show up here. So if I hover over, it's 6.5, 5.5, blah, blah, blah. So each one of the inputs to here is a version of the reference voltage, and here it happens to be 7. Okay, and then I have comparators, and those comparators are going to compare my input voltage, which in this case, for this example, is a ramp function, okay? And so you're trying to make it a slice every instance you're making a slice, but here we're looking at the binary output. And then this is just your priority encoder, a very simple one. And so as we run through this, you can see that we're ramping up, and then the ADC values are changing here. And we could go and correspond to say when this is at VDD, or when this is at the highest voltage, is this at 1111. What questions do you have? Yeah.
Gradations. You just make it.
For this particular one? There are more efficient architectures. So you're coming to one of the challenges of this particular architecture is that you're going to need to have a resistor for each gradation, and you have to have a comparator for each gradation, right? And you may not know this, but resistors are actually really large on pieces of silicon. Like they take up a lot of real estate compared to like an op amp is actually pretty small. Or even a comparator. Comparators is about the size of an op amp. Digital logic's even smaller. But these just consume less of power because they're making this decision every single cycle. They're making this decision. What other? Yeah. So this would not be an architecture that scales well.
Yes, instead of like having like a constant increase in VREF
Yep.
for each scale, couldn't you do like half of VREF and then a quarter of VREF and an
Ooh,
eighth?
like a binary search sort of thing.
Yeah.
We're going to get to a version of that. But this is one of you wouldn't do this with a flash ADC. But yes, there are better ways to kind of find your value. Yeah.
Give me an example of like an input and an output where this would be useful. So I'm sure it is, but I'm just like trying to figure out.
What are you asking? When is an ADC a good thing?
No, I'm saying this kind of ADC.
Anybody see any advantages to this ADC? Say it another way. How long does it take to come up with an answer?
It's just like gate delay, there's no clock or timing.
Right. So these are really, really fast. That's the big value of flash. And we gave you a hint. They're called flash ADCs. Okay. But this is less than a clock cycle. Guaranteed, you're going to get this answer. So we use these in We use these in sometimes things that have to sample really fast. So like, oscilloscopes, especially high-end oscilloscopes, because you don't want to have to wait for something to, as we'll see in other ones, to do a binary search and find the value. Does that answer your question? Okay. Any other questions? All right. This is one of the most basic ones. Very popular, one of the early ones, but it does have limitations. Let's talk through those. No. So speed we talked about, it's very fast. It's only the propagation delay of the comparators and the priority encoders, which is basically always going to be less than one clock cycle. The resolution is limited by the number of elements in your ladder, and that's going to be prohibitive at large values. Complexity, I mean, in some ways it's a simple design, but you do need lots of things. You need n resistors and n-1 comparators. That's actually a lot of components that are required to get this done. Power consumption, so is there a power speed trade-off? Yeah, I guess if you go, I don't know what I was thinking when I wrote that slide, but yes, if you go slower, you do get a power savings. You're not always burning it because it's really about those comparators making the decision. The resistor ladder is always consuming power, but it's probably less than you actually think. All right, let's go on to other architectures. Another classic one is a slope integrator. So the idea of a slope integrator is that we don't want to use a lot of hardware to make this decision. So the last one was like, we're going to use a lot of resistors, a lot of comparators, and make this thing happen at one time. Here, we're going to use time as a variable. So time is going to help us, allow us to figure out, to measure things. Remember, microcontrollers are really good at measuring time. They're bad at everything else. So use the analog ramp function. So imagine if we had something that was ramping up at a known rate, and we just said, okay, when my ramp function equals my V in time, whatever that is, then I just go down and look at that point, use a comparator to detect that, and then just go read off the time. So here, you have some nice ramp function, magical ramp function made in analog, and you're just ramping this up. So here's your input voltage. You're going to have to sample and hold it because you can't wait. You don't want it, the analog voltage to change, so you have to sample and hold it till it comes to that point, and then you just do a ramp function. And now if this slope is known, then you can go and calculate how many clock cycles went by and figure out what the value was. So this is has some good advantages. Let's see. So we talk about how do you make a hardware slope generator. So we talked a little bit about this RC charge up. This is not what you want, but this is typical of, this is a type of ramp function. So here you have a voltage value at time t, you close the switch, and then your capacitor charges up. So not what you want. But maybe if you have taken 215, you might know that if a current source of a single current value, so a known current value, a constant current value into a capacitor will have a slope that is constant, right? It's not an RC charge up, this is going to be a constant slope up until the voltage, not shown here, up until some, well, I guess voltage max is the maximum voltage that current source can provide. And some people might be saying, current sources sound insane. How could that be a thing? I've only used voltage sources. Yes, that's true. They're insane. But in the world of integrated circuits, they're actually super easy to make. You just use a current mirror pair, and you can have as many versions of a current source as you like. It's just not, in this macro world we live in, we just don't often times use them. Okay, so any questions on the basics of making a ramp function? You're just going to take a current source and dump it into a capacitor. Yeah.
Could you somehow make an electronics thing that just changes the resistance of something so that you can measure voltage and then you can still have like a linear ramp function? Because like voltage versus the resistance is going to be a linear relationship, right?
Yep.
So is there like a component that does that instead of using the capacitor, you could like swap out for that?
You want a variable resistor is what you're saying?
Yeah, but like I guess electronically controlled variable resistor.
Yeah, I mean, such things exist. I'm not sure exactly how to use it for an ADC yet, but the way they make them is basically they have lots of little resistors, and they have an analog feed network that allows you to tap off to different versions, and then you send it like an I2C command, and it will actually change its equivalent resistance.
I see. So you're kind of like hopping resistance.
Yeah.
You're not like sliding.
So it's like, yeah, it's like that voltage ladder, and you're just choosing which tap you're connected to.
Gotcha. Thanks.
Yeah. Okay. All right. So I made this overly complicated. I got too excited. Okay. Let's see if it. So what are all the pieces here? So I've got a magic current source. We didn't actually tell you how to make this thing. That's an analog circuit design course, but I have a magic current source, and it feeds into this capacitor. You have this is not how you would do it in the real world, but this is how I did it. There's a little gate here that discharges and charges that capacitor. All right, so we have some input value, some ADC analog value in, and this thing ramps up, you can see, to some value. Have some control logic that's keeping track of things, and then it's going to show you the binary number, the number of clock cycles it took to get to this value. And so if I go and increase the voltage, see it took longer for it to ramp up. And I don't know, something weird happened because I probably changed it on the fly, didn't like that. But we're counting up, and now you get the value of 10. Okay, and then I can go, if I had a really, this can go all the way up. And now I get a value of 24. So what's one way to give me more resolution if I wanted to? Yeah.
You can slow it down, provide a smaller current. It takes more clock cycles to get or like each individual clock cycle is a smaller change in voltage.
Mm-hmm. What's the opposite of that? That is the opposite, but again, I did a bad job telegraphing what the answer I was hoping for, but I happen to have a slider over here that does this. And so I can reset. And now, just by increasing the clock speed, right, now I've gotten to I got a higher value for the same number, and now I can actually use time. So remember, right, microcontrollers are really good at measuring time. They can go really fast. And now I can use time to get more steps into here. Now I can have more resolution. It's still the same voltage value, it's just more resolution to get that voltage value. I see confused faces. Somebody's got a question over there. They're like, this is black magic, stop it. Okay.
It's just slower but more accurate than, for example, the flash ADC. It
Correct.
uses like instead of having set like voltage dividers that go along, it just, I guess, goes along a slope of increasing voltage through that mechanism that you
Yep, you have some other timekeeping device in a sense, and that is this slope. So that current has to be particularly accurate, and then you get it to this value, and then you just have one comparator. So it's a slope generator and a comparator, and then the digital logic doesn't really matter. Right? That's free.
What is that number though?
Some number. The value that's represented by that ADC. So if I go and change the voltage here, now it's 32, right? And so that is some digital number that represents how many clock cycles that have gone by. And now we can convert those numbers into some equivalent voltage. So just like an ADC, like the flash ADC would give you some binary value that represents that scaling between negative ref and positive ref of the voltage signal in there. This is a different way of doing it. We're just using time. Yeah. I just have a reset thing. I have to go and reset for it to cycle over and over again. I just have it reset here. But some of this, like this digital control logic, you don't have to worry about. And then this is just a binary counter. So I have some clock there that's spinning away. And then we're going to keep counting until basically all this control logic does is when this value hits this value, it stops. Yeah.
I'm sorry, is this only valid for a ramp function where you know what the behavior of the ADC is?
Sorry, is this only valid for a known ramp function? Yes. And that is one of the challenges with a single slope integrator, is that it is more sensitive to noise and process skew and these other things, right? That ramp up should probably be calibrated in the real world. So a lot of your chips, like the oscillators, are calibrated at the fab. Your ADCs are actually, and DACs are actually calibrated at the fab. So there's a register that says, here's what the offset is. And so that means during test time, they made this die before they even put it in a package. Typically, they'll put probes on it, make sure the chip functions, yes, and then it'll go through and calibrate it for any offsets it may have. Those offsets come from process skew. Sometimes, I don't know, it was a little bit warmer, a little bit hotter, whatever it was when they're fabricating that chip. All right. So the big takeaway here is we're going to use time to measure an analog voltage. Before, we just used a lot of parallelism of analog circuits, and here we're going to use time. The takeaway is we only have one comparator and one slope generator, which is actually pretty low power. I will bring up the fact that the dual slope integrators exist. Knowing what you need to take away from this is why would you choose one architecture versus another architecture, how you actually make a single slope, dual slope. The differences between them are probably not as important, but you would need to be able to recognize the architectures between flash, slope integrators in general, and then ADCs. The trade-off here is that what it does is it has a charge up and charge down cycle, and this makes it more immune to noise and process variations. This covers up most of the issues that you would see with a single slope integrator. So a dual slope integrator is what's in multimeters. It's a very low cost way, low power way to make an ADC, but you're trading time. It's not going to be very fast. So for those that get real interested, you can go follow the Falstad and look at that one. But basically, the takeaway is there's a charge up and charge down cycle to deal with the variations in your ramp function. All right, so slope integrators in general, the issues here, we have speed. So they're relatively slow. You're using time to measure this analog voltage. So it's going to take multiple cycles. The resolution can be pretty high, so that some of the highest resolution ADCs are slope integrators. They're just slow. So you can get I think it's actually, I've seen 7.5 decimal or digit ADCs, multimeters. So that's the type that they use. So it's high resolution. Complexity, I don't know, maybe medium. The analog ramp functions can be hard to make, but in silicon is pretty easy. And then power consumption is good. This is good for battery-powered things, multimeters, those sorts of things. All right, any questions? All right, so the last one we'll go through for ADCs is a SAR ADC. So this is a successive approximation register. I'm not sure why they use the word register there, but they have, and I stuck with it. And so the idea here is you're going to do an analog search, basically an analog binary search for the value. You have some reference value, and you're going to test to see if your value is higher or lower than that. Now, we've done you a small disservice. I've cheated. We put a digital to analog converter in here, and I haven't told you how those work. So you're just going to have to trust me that they exist and they work. But basically what happens is you have a sample and hold circuit. You're going to hold it. You compare if your DAC value is greater than or equal to, and then you have some logic that says, okay, now I'm going to search. And then your DAC says, maybe DAC starts off at like 50%. It says, is it higher or lower? And then there's a binary search down to the next value. Yeah, so you're just comparing. Again, you're using this comparator to make judgments. That's the other key of ADCs, is that comparators make all the judgments, basically, if if one value is bigger than another one. I don't know any ADCs that don't have a comparator in them. Okay, so for the logic here, the binary search logic is basically saying you're going to start off with 50%, and then you're going to say, is your VIN greater than your DAC output? And let's say it's not, and then you're just going to keep on going through this cycle, and you search again. You're going to do 111 or 0100, a smaller value, and you're going to keep going through that bit to find out a value that it is. Eventually it's 1, let's say, and then you're going to servo to a particular location. So here is your sample time, let's say. You've sampled, you're holding, and now you're doing this binary search that searches for that value.
What's the advantage of this over the, I don't know if I'm jumping the gun here, but what's the advantage of this over the dual, because this is going to take a decent amount of time, or will this take less time?
This will take less time because now we're doing a binary search. So I need less clock cycles to converge on an answer. Before it was basically a linear search. I just go for the whole time until I find the value. And because, just the realities of making peripherals, you're going to go for the longest possible time. Right? It's unlikely that you'd make a peripheral that is, if it converges early, we're going to throw up an interrupt. I mean, maybe you could, but typically how ADCs work is they just quote you the longest possible time, and then that's your maximum sample time. Because then they don't want to have to do things like, it just doesn't work. Like, I want to go as fast as I can, and it's the longest possible conversion time. So this one will convert in however many 2 to the n bits, I guess, or how many bits you have. So let's see. Now this one's a little bit, here it is. It's a little bit buggy, but that's okay. Let's try it out. So basically, we're gonna have some value here. We're gonna turn this thing on, and then we're gonna get 4 clock cycles out of here, I believe. So let's see. Let's reset and start. All right. So, it's 4 clock cycles because it's 8 bits. So in 4 clock cycles here, this is the clock. This is just a special circuit that allows me to put 4 pulses out. And we can look at the end, we can look at the value in the final clock edge, what came out. And here, you can see that it was searching. So this is the output of the DAC, is the red line, I believe. So where's my DAC? Here it is. Yep. And so the input voltage was, here's my input voltage. So my input voltage is here, and then my DAC went here. said, okay, I'm smaller than the input voltage, jumped up by a half, jumped down, and then went through. I don't know what happened there. Maybe there's a little control logic error, but it should have converged and just stayed at that smaller value. We can set this thing lower. Let's see if it works. Reset. And here we've converged, and it still made the same error. Well, that's what you get from using Professor Sample's Volstads. But the general idea is it's searching down for this. It must have an off by 1 error down there. So what do you think some of the advantages and disadvantages of this ADC type are? All right, talk amongst yourselves. Take a minute to figure out some advantages and disadvantages.
The logic driving the DAC is pretty expensive.
I was gonna say,
Or it's using software.
expensive, but it's fast as hell.
Well, it's slower than the Flash though.
Well, the flash is it's fast and accurate. It's a
Yeah.
great PA.
And then I would imagine if you want your oscilloscope to be really fast, what you have to do is you have to have multiple of these. Do the voltage sampling, and so you have like an array of them. Like for like this is like 1 nanosecond, 2 nanosecond.
The big drawback is just that the DAC is like.
All right, what do you think? What are some advantages and disadvantages of this type of ADC? Yeah.
It's like a foundation to include accuracy.
Yep. Yep.
Reconfigurable as to the precision and the speed.
Ooh, tell me more about this.
So you could change how your binary search thing works by maybe saying like what your step is on your DAC, and then yeah, that's the only way I can think of changing the speed and precision. But I can just
Well, you could say that was a 16-bit. You could go less. So 16 bits would have a certain amount of time it would take to converge, and you could go less time, right? You could go to 8 bits if you wanted to, and give up precision for speed. And that sometimes is a valuable trade-off. Yeah.
Wait, what are we giving up? Are we giving up the less significant bits?
Yes. Yep. I suppose that's actually interesting. If you knew where your signal was going to be, you maybe could like purposefully use a binary search just for that area, but you'd have to know where it was, which kind of defeats the purpose. Yeah.
More expensive, this or flash?
This or Flash? Flash is more expensive. Modulus, that secret DAC part that you don't know about yet.
So I was wondering about that, because that's probably, I don't know,
It's actually still going to be less expensive than a Flash ADC.
power consumption.
It'll probably be less than an ADC because you only have one comparator. So this idea that you can trade off accuracy for speed is actually pretty useful, and your microcontrollers, the STMs that you're using in lab, actually have all their SAR ADCs, and there's also another type called Delta Sigma. But SAR ADCs are very popular, and they actually give you this trade-off. So we can look at the slides later, but you can get like, I think it's like double the speed by going by using the lowest resolution settings. I think I have that slide later. All right. No builds. Okay. So speed is a binary search. So if there's a balance between conversion speed and resolution, it can be medium to high resolution. So you can spend a lot more time. The more it's the resolution of your DAC can help you get to higher resolutions. Whereas a flash, you're really limited by the number of resistors you're going to have and comparators. So more versatile. Complexity, you need a DAC, but the control logic is pretty simple. And power consumption's, reasonable power consumption, so somewhere in the middle. So for you guys, it's probably important to realize what's the thing that you need to take away, what do you need to study? So understanding the big difference between trade-offs of ADC types. So things like, one is a voltage ladder that makes this very fast but expensive in terms of space and power. Another one would be that slope integrators use time, and SAR ADCs are using binary search to overcome some of those disadvantages. So you should be able to say which one would you like to use for a particular application. If you really want to know more about ADCs, that's an analog circuit design class, and it's probably good to recognize that the simple circuits that we showed you here are not, and they're good for teaching concepts, but a real ADC is much more complicated, mostly because you're trying to deal with figuring out how to make like the slope integrator circuit or all the bias circuitry that needs to go into it, dealing with things around manufacturability and process noise and process speed, and just dealing with noise in general. All those things make ADCs much more complicated. So we'll go through, do a little exercise. We'll figure out what are the trade-offs between different ones. Just to make it cemented. So you could just think of this less as about some absolute value. It says where are the cons and pros and cons of each one. So maybe just rate them in terms of high, medium, low. Yep. And one more. There you go. So really the trick is you're basically trying to compare them against each other. So high, medium, low, something like those ratings would be fine.
Just like low, high speed, high medium low based on
Yeah.
Flash could have like
I wouldn't even
high.
But it can't because there's practical limits like size.
Yeah.
So you're pretty much limited by what practically can be built.
Yeah, so many years, yeah.
Like accuracy depends on how many average slides you have.
It's configurable.
Accuracy.
Somehow what happened was I got one question.
We're gonna get the right answer. Slope integrator is medium. I'd say.
But like they all depend upon how much resolution you want to have.
Even though they were like,
Oh wait,
But-
accuracy
but-
versus resolution.
Consider potential of SR versus the potential of flash. If you can configure SR to be.
But no, that's resolution. Accuracy is like how well you adhere, like
I think in the binary search, always comes to the correct answer.
but like in perfect situations, they all come to the correct answer.
It's not flash.
It's not perfect. It's only when you have low resolution. If you have
This is
super high resolution because you have a bunch of voltage divides,
Okay.
you can get as accurate as you want.
Okay, so I guess if you're saying, okay, I see what you mean.
Yeah, like I'm not proposing an answer. I'm posing another question.
Yeah. Well, then it's not
We
resolution.
can do complexity.
We do resolution, I think, right? Because resolution.
These are all configurable. So this
Flash has the highest
resolution.
Flash is a
I think inherently slope integrator is always going to be slower than
It's only configurable in hardware.
Yeah.
Like, whereas this stuff,
high, low, medium.
it'll be much higher. Plus the goal is speed, so you don't really want a lot of resolution, or it's gonna take long.
I can see that. I see what you're talking about the configurability. Complexity, flash is low, complexity, costs high.
To do like medium, low,
High, low. Like for speed, right? There's definitely, no matter kind of how you configure them, there's one that's fastest, there's one.
What do they mean complexity though?
It's not supposed to be super deep, there's nothing to calculate here.
Medium, high, is not, it's very complex. It's a very simple idea.
Simple idea.
Like, yeah, I don't know which one they're asking though. Simple idea, a lot of hardware.
Yeah, so I think that's what's talking about cost. Oh, you know what? Yeah, right. We wouldn't be talking about the complexity of like. That isn't specific enough.
I think this is low because it has, I'm assuming, lots of hardware. You have to to have like all those comparators.
Yeah, that's what I.
Yeah.
And then
The power of Flash is gonna be
effective accuracy, I should have talked about high, small, medium, high, plus DAC.
SAR is 2 on power, I know that.
You could have this high resolution, but have.
No, I'm saying high complexity makes this the best variation, even though you have.
A high complexity? Use a binary search.
Because you don't have like a million comparators, but you do have a DAC. And you have the DAC and the comparator, which this just has the comparator.
I should have talked about in terms of accuracy was that getting R's to be equal is non-trivially hard in silicon. And so the best, and this will come up more in DACs in a minute, but there is challenges like if this one's a little bit smaller, then your whole ADC is a little bit off, right? There's no guarantee that they're gonna be exactly the same value. So that could be an issue with Flash ADC, that it has accuracy issues. Although I'm not suggesting on a test that you would immediately know all about analog circuit design to figure that out.
The accuracy is. It depends on the accuracy of your comparator. I don't know.
Integrator has it's low power, right?
It's the accuracy of the comparator and the DAs and the DAC.
You're saying SAR is medium power as well, right? It has
Accuracy here, the DAC might make it.
Okay, well, yeah, he said this one definitely takes the most power, right?
Yeah.
Because it has,
It's complex. Do you guys watch
Yeah, see now I gotta write in all my boxes if one means the most complex or the least complex.
What's like the best?
No, one means best, whatever the best case is.
Too high, you forgot. Oh, you don't. See if we can argue it through. We can come up with the correct answers. What about resolution? Which one probably has the highest resolution, given some versions of things that are equivalent? I would argue it's slope ADC, right? For the designs, well, resolution, if I could go and add as many resistors I want on there, right? To get higher, it's just that you come up to practical limits of nobody's gonna build that, right? You just get into 12-bit flash ADC, there's a lot of resistors. All manufactured correctly. The more complex your design is, the more likely you're gonna have errors too. So I would say flash is that, or no, so slope is the highest resolution. What about flash versus SAR? Intuition.
I give them both medium because it just depends on how you configure them. With SAR, it's like really configurable as to how many bits you need for everything, and then Flash is like how much you can afford, basically.
Yeah, I don't know when I did my builds the wrong way, so I did them by device rather than this way. So we look at my answers later on. But that feels about right? There's no inherent reason why one is much better or much different than the other one, Flash versus SAR. What about speed?
Fastest.
It tells you it. I gave you that. It was a free points on the exam. It says it right on it. It's the fastest. What about slope integrator versus SAR?
Slope is
Slope is the slowest, but it was, it has the advantage of it's the highest resolution, right? So there's trade-offs to be had when choosing an ADC. Accuracy might be hard to figure out, but what's a guess? What do we have a guess here for accuracy?
Slope integrator is the most accurate.
Okay? I think that's about right. We can make arguments about why one would be more than another one, but slope, certainly you only have one thing to screw up. It's not relative to anything else. You get your Slope integrator has some rise time to it, and you might have to calibrate that, sure, but it doesn't vary bit by bit. While a flash ADC, those resistors may be malformed. It's very hard to get them all the same size, so you might find out that one bit is a little bit smaller or a little bit bigger than another bit from the analog point of view, because you have multiple things you have to get right. And then I put the SAR somewhere in between those. All right, how about complexity?
SAR was the most complex, slope integrator was second most, and flash was the least complex.
Depends on, I guess it depends on what I mean by complexity. Yeah, so flash is certainly, you had the most involved digital logic. If we're talking about control algorithms, and that's certainly the most complex. And then slope integrator is probably is in the middle, and then SAR is pretty easy. But I guess somebody might argue from like an analog circuit design point of view, which is the most complex. Well, in that sense, the flash is probably pretty simple. So, okay. Power, what do we think?
So I think the flash is definitely going to be eating up the most power.
Yeah.
Just because you have a lot of stuff going on. And then I gave slope integrator and SAR both medium.
Okay.
I figured they're both comparable, and they're kind of trying to be efficient in their own ways. So
I think that's fine. I think slope integrator ekes out SAR a little bit, but it has less. We'll see in the DAC. You have secret information I don't know about, which is the DAC. DAC's an unknown little piece there, but yeah. They're not far off from each other. How about cost in terms of area?
Flash is highest because of the resistors.
Yeah.
And then slope is lowest because the current mirror digital logic is pretty small. And then
Yeah.
SAR is medium because the DAC is probably pretty big.
Yeah, that sounds good to me. Let's see. Again, I made these builds sideways or vertical instead of horizontal. Let's see, do I believe any of my things I said last year? Power, okay. Complexity, okay. Anything you guys disagree with? No? All right. So two other types of ADCs that are pretty common. And we could just talk about ADCs all the time, but probably not the goal of this class. Delta Sigma are very popular. They're a 1-bit ADC, and then you have this analog summing thing that takes the analog voltage you have in your SAR ADC output, and you have a little integration function. You don't have to know how it works, you just have to know that it exists. Okay, so this is simpler, has some trade-offs and disadvantages, a little bit simpler than SAR ADCs. The pipeline is interesting. They're kind of a cousin of each other because they both have the summation block there. But this one is doing like the first 3 bits and the next 3 bits, and successively getting down to, I guess they're using a flash ADC for the very, very end. So just know that these exist. When you're on a job interview and they say, they didn't teach you Delta Sigma, you at least say, told me it exists. Okay. So SAR ADCs on your STM32. So there's your awesome block diagram. Basically, you have a SAR ADC, and then you have all these helper circuits around it to do tasks. And most of them are triggering, interrupts, those sorts of things. So this is a 12-bit ADC at 5.3 megasamples per second. It's pretty damn fast. This is why you can go on Amazon and buy really, really cheap oscilloscopes, right? It's basically just a microcontroller with some over voltage protection circuit on the front end. You know, it's very simple, but 5 megasamples per second is pretty darn good. It's pretty cool. If you go half the resolution, you can go much faster, so 8 megasamples per second. It's pretty amazing. You get external channels, sir. So external channels are basically pathways in, so you can use one DAC for multiple pins, and then they're just going to be routing those analog signals from those pins into your ADC, which is pretty cool. And then they each have their own sample and hold circuit. So you go and sample and hold something on pin 1, and then you can go and take a conversion, then it switches over to pin 2. I think on yours, how many ADCs do you have? I think you had more than one. Maybe I'm thinking of the ESP. But you have 5 internal channels, internal voltage references. So you can use battery, you can use a version of the battery divided by 3. There is a temperature sensor in there. Making temperature sensors on silicon is almost free. Basically, you just need 2 dissimilar diodes and putting the same current into both. And doesn't matter, the slope of those 2 curves are proportional to absolute 0. And so almost any piece of silicon can give you analog, or give you temperature. Internal voltage reference, you can even use the DAC outputs and route them internally back into the ADC as a reference for your ADC. Kind of wild, but yep, it can do it. And you also have oversampling. So say you want to do smoothing, you have a somewhat noisy signal. It will automatically smooth out those signals for you. And when it's so, normally you'd have an ADC conversion, and you can throw an interrupt, and then you go pull the data out of that register. But say you have something you have to average over a period of time. Well, you can have the hardware average it for you. So it'll converge, take a measurement, put it in a buffer, add up 16 of them, and then throw you the interrupt. And now you have, it could be, I think it's 16, there's divisions of that as well. So now you can do some basic analog signal processing on your peripheral without having to go all the way to the core. And finally, which is kind of cool, I had never seen these before. I looked at the ADC, the STMs. They have 3 analog watchdog channels, which means you can put the whole thing to sleep. And if an analog voltage gets above a certain value, then you do something. Then you throw an interrupt and do something. So it's like this, instead of just having an interrupt that works on a digital I/O pin, when this thing rises, throw something. It's when this voltage goes over a particular value that you do some tasks. We don't really talk about low power here, but that's a pretty cool function if you're trying to keep your core asleep, or maybe you had some really other complicated tasks to do. You basically have this thing looking at an analog value. What else? Any questions? Trying to figure out what I actually want to teach you. Okay. So you can also program how fast the ADC can go. So you have whatever your clock is, you have a clock going into it. You can pre-scale it down and then have that be the time it takes to converge, so you get some control over that. It does the binary search we talked about before. You have a homework assignment on this. So if you want to figure out what your maximum sampling speed is, you can go through and figure out how long does it take to sample, right? That's part of it. How many clock cycles does it take it to converge? And you probably want to go for the worst case scenario. So here we say it's going to take 4 clock cycles to sample, and for 12 bits it's going to take 12 clock cycles to converge. So now you can go into, you get 16 cycles in total. In this particular clock speed, which is very nice, you get 1 microsecond. You can go much faster, right? If you can go at half the resolution, but you're still paying for that sample time. So that's a constant that's not going away, even if you reduce your resolution. But still, that's pretty good for a 16 megahertz clock. And then, if you get real excited, there's on your device, there's different data output type modalities, right? So you can say, hey, I want you to take my 12-bit value and put it in the highest bit first, most significant bit first, and just leave trailing zeros here. Or you could say more a right aligned is what we might normally consider it to be. It's just to point out that you have lots of different options of how you do it. The 8-bit is probably the most relevant in the sense that now you could pack more data in one word than you could normally, right? Rather than having a word or a memory location for each individual thing, or a word for each individual value, you can pack it at one memory address. But just to know that there are output types if you get confused or start looking through the data sheets. We talked about this a little bit, but the injection channel, the regular channel is you have your GPIO ports. Remember, you go through your GPIO ports, you configure them. You have alternative function is usually one of the parameters, and that means you can take that value in analog value or whatever the value is and ship it somewhere else on your device. So you could ship the signal to your UART, for instance. That's your reconfiguring your GPIO pins to act as the UART input. You can do the same thing. You can send analog signals through your GPIO pins, configure that, and send them into here. You have a regular channel, which is basically take an ADC value and make a conversion. You have these 4 injection channels, which basically lets you round robin into the session. So you go 1, 2, 3, 4 as fast as possible without having to tell it to take a new ADC measurement. So for the regular channels, you basically take ADC measurement, wait for interrupt or some other event to occur that tell you it's done. This one will take them successively one right after another. So you can get 4 channels kind of pipelined, working quickly. These are probably more a reference channel itself, not necessarily what we're going to talk about. I mean, not important for like an exam. This is if you want to use your ADCs. Those. So the STM allows you to control your input references. It's not always going to be 5 volts. We talked a little bit about this. You get the internal voltage reference. Internally, it will allow you to have a build for it. So how does the internal reference work? Basically, it's a band gap generator. It's a silicon structure that will give you a reference voltage that's always constant, independent of the voltage that's being applied. So if you have a lot of noise in your system, which can happen because say you have a lot of UART traffic going on or SPI traffic, those current spikes will corrupt your signal. And so if you're finding that your ADC measurement isn't accurate enough, you could use your internal voltage reference. And that will allow you to control the top end over there. It doesn't really do anything for the bottom end. I don't think your microcontroller can actually control the negative V. You don't have an input for your negative V ref. All right. And I think I'm going to end there. We have a little bit of time. I'll start with DACs. But to recap, we talked about flash, slope integrators, and successive approximation. You should be comfortable with those analog building blocks. There's 3 of them essentially. We talked about sample and hold. You should know why that exists and what you can do with it. Comparators in general, just high level, how do they work? And then the voltage divider. Those are elements, fundamental trade-off, or fundamental elements of all ADCs. We talked about how ADC, you should understand the ADC trade-offs, and we talked about some aspects of your STM32. All right. I'm going to take a 1-minute break, and then I'll start on DACs.
Yeah, I don't know why.
Give me $50.
Instructions, please indicate what you do. Yeah.
Do you want to show up to the lab a little early tomorrow? I have something afterwards.
I was actually going to ask if you wanted to show up a little late.
Text that out here. Let me see.
Yeah, that's tough. Yeah, so I have something from 3 to 3:45.
Yeah, that's fine.
So then my question is,
Why don't you just start, and then I'll show up and you can hand off to me.
And then you'll stay.
What does it do?
Probably a week after our lab. That way.
I don't know if Thursday is good because we have a meeting for another class which hasn't been scheduled yet. It could be Thursday.
Okay. This is cool.
What does it do?
For the first little bit of this lecture. Go. All right, so talk about DACs. Before on this page showed you where the reading material was for this material. So DACs can be thought of as your function generators. So function generator, just another piece of lab equipment. You tell it what function to put in. You want a sine wave, a square wave, and it says, what's the frequency, what's the magnitude, and sends it out. That's essentially what your DAC is doing. The most common DAC you guys are probably used to is, your speakers, your audio output. These are highly optimized devices that don't actually play nice like normal DACs or ADCs would. So microphone input versus ADC. ADC will give you the raw value. Microphone input, usually the hardware is doing a lot of shaping and makes a lot of assumptions about how the audio is coming in because it's specialized for that particular bandwidth. But effectively, in this case, a DAC is just a speaker that's playing a sound. For your DACs, you have some binary value that comes in and it's going to convert it to an analog voltage. I mean, this is not going to be a sine wave. This is going to be, for every one value, is going to be a single analog output, but you could time vary it to make a sine wave. Sure. And then this is the same mathematical logic that we use to formulate ADCs, right, to figure out for some analog input what's the equivalent binary value. You can do the same thing in reverse and figure out for a given binary value what the analog output's going to be. There are some issues that you have to think about with DACs that don't really come up with ADCs, although we did talk about sample and hold, which is equivalent idea. So when you think about loading effects, say you have your ADC module, and then you're trying to drive some load, right? So this could be literally the resistor in your speaker, or it could just be, something high value. I think maybe an LED or something is possible to do it with a DAC. Usually we do audio things, but this is usually pretty large. The resistance is large, meaning the current drop is small, but sometimes it's significant enough to corrupt the output voltage. So you have your voltage desired and you have your output. Unfortunately, there's this resistor in between, and this is a parasitic resistance. This means that your DAC module doesn't have the strength to drive current out here over any load, and you'll get some drop in your output load. And so the way most DACs deal with this is by adding in an op amp in between. So here you have your desired voltage that comes out. It has some source resistance built into it. You could have a capacitor if you wanted. It's not required. Your op amp's going to say it doesn't allow any current to go through that input. It's basically very high impedance, high resistance. So all this voltage follow circuit's going to do is whatever's on the input is going to mirror on the output. So this basically separates the voltage divider, and it gives you V desired is what is going to be on V out. They're approximately equivalent, very close to each other, regardless of what your loading value is. So if we go look at an example of that. So here we're trying to output 5 volts, that's what desired. There's some parasitic resistance. For some reason our DAC just can't push out as much current. It's not infinite amount of current, it's some smaller amount of current. And here we're just representing the equivalent circuit as having a resistor in series. There's other ways to draw equivalent circuits. There's no real resistor in the real world. And here, so here's the voltage. You can see we put 5 volts in. Here's a kilo ohm as our load resistance, which is actually pretty reasonable. Kilo ohms is a pretty large value. Speakers, for instance, are much lower, maybe 80 ohms or 40 ohms. And so here you get some voltage drop, and you can see you wanted 5 volts, you got 4.5 volts. Here, you've broken up this voltage divider. And of course, op amps have output resistance, but the feedback tries to cancel that out. And so in most realistic conditions, the input voltage, desired input voltage equals the output voltage. And we can play with this a little bit. So these should be tied together, if I did this correctly. So here the load resistance increases. Ooh, look, they all resist the resistance. So this increased, because this is becoming much larger, I'm getting closer and closer to the max. Right, so now it's very near 5. But if I had something small, right? So here, let's go really small. 700 ohms here. Force it to be small. Let's say 100 ohms. But this one didn't update. I try this one too. The op amp is providing the current. So this voltage is still 5 volts, but over there it's 2.5 volts. So you need this little circuit in between. How many people have taken 215? You all knew this? Is it boring? You've fallen asleep? Okay. Fine. I'm glad you all took 215. Now I get to put more questions on your exams about analog circuits. 215? No. Oh, you said I stopped being an ECE student. I came over here to computer engineering to get away from that nonsense. This class, you only have to know about the intuition about what's going to happen. You don't actually have to calculate anything. Okay. So these loading effects happen all the time. All the time, all the time. And just knowing the tricks that there's a resistance over here, especially in RF, where that is the important part. All right. 5 minutes, I'll do one more for you. All right, so the simplest ADC in the world, or DAC in the world, right? How about we take PWM and just filter it out? Filter. Try to filter over it. And now you can see, you can imagine that when you have high voltage coming through, your signal is going to be very high. And if you have low voltage coming through, the signal is going to be very low. So let's look and see how that would work in the real world. I guess another way, the more accurate way to look at this is you're going to put a square wave into this filter, and what's going to come out is a distorted, somewhat slightly distorted sine wave if you varied these voltages sinusoidally. So you're varying the duty cycle sinusoidally, and you get a sinusoid out. Wow. And this sort of ADC is like what most buzzers are, like little things that beep, make 8-bit sounds. It's pretty simple. So here we have the output voltage in blue, and here you have the input signal, and change the duty cycle. So here it's pretty high. Mostly once, duty cycle is like 1% here, so I get a voltage that's very, very high, and then I can go and change it down. I can get 50% if I want. And so you could imagine I could change this duty cycle sinusoidally and get a tone out. What are some disadvantages of this? What's that? I don't know. It's probably pretty good on power. Well, let's compare that to some of the other ones you're going to see later on. So come back on Wednesday and you can tell me if you think it's good or bad. Yeah.
I don't know if I can call it noise, but it's like it's not smooth. Like it's jittery.
Yeah, and there's kind of no way to get out of this. There's always going to be some amount of harmonic noise on this. You could say put multiple filters on the output. You could increase your frequency if you wanted to, but there's always going to be some amount of distortion on there just because you have this RC discharge that's going to occur. But otherwise, it's pretty simple. All right. Any other questions about?
Like, it doesn't look super responsive. Like, we changed to 50%, it took a while to reach this.
That's true. I mean, here, I'll go like this. It's getting responsive now, so your statement isn't wrong, it's just a relatives comment as well, right? Oh, I don't know what you guys can see up there. So, yes, it takes multiple clock cycles, but if the world is fast compared to you as a human, compared to the thing you're trying to interact with, then maybe it's okay. So it comes down to your application.
Only.
One last question. Somebody has questions. You guys do Falsat in 215? You guys do Spice?
Yeah.
Which is better? See, I won one. I got one. All right. Thank you. Have a good day.
Wait, have you taken it?
No, but Spice.
You've heard the horror stories of LT
Your sheets, please.
LT Spice. I never really heard that was bad, but dude, it's just ugly.
I didn't even have
Said the voltage.
Okay.
And and there are transit teams that will do that task. Let's talk about it right after this.
Wow.
Damn.
This guy.
No, I'm serious.
I've never actually been.
Like, those were the exact same spot.
Talk about some random shit.
Captain America.
Thor. Oh, sorry.
I mentioned I need to measure mine.